Hello, everybody. Welcome. My name is Michael, and I hope you're having a great day so far. Today, I'm going to be diving into data structures and algorithms in Python. Thus far in Python, we've learned the basics. We've learned about functions, loops, importing modules, files, debugging, all that kind of stuff, testing, etc. Now, we've even built a few projects, such as the beginner inventory tracker or management system, and then the most recent, which I'm really proud of, is the task tracker project, which is complete and can be found on GitHub on a shareable repo, where you can clone and get access to your own task tracker and use on your own system locally. Um, so feel free to do that. The link for that is in the description below. But I believe I'm at a point where I've learned the basics and I've applied them to some projects, and now I'm ready to dive into some more intermediate and advanced topics. Now, these might not be intermediate or advanced for you, but in my terms and in my viewpoint, these seem pretty intermediate and advanced. So just take that with a grain of salt if you're watching and following along with your progress. If you're finding that this is a little bit too hard and you're not following very closely and you're finding you may be getting lost, feel free to go back and maybe take another jab at the Python Crash Course Part 1 and some of the videos on my channel where I taught myself the basics of Python and how to use it and run projects and create your own projects basically. All right. So this is data structure and algorithms in Python. So I'm going to take notes here on the right side of my screen, and then I'm going to just go through the book. So let's go ahead and pull up the Discord. Feel free to join the Discord if you would like to stay in touch when I'm offline. But yeah, let's go ahead and get started here. So I'm going to read pretty much word for word in this book. I want to get everything. Of course, this beginning stuff is kind of arbitrary, but all right. Preface: the design and analysis of efficient data structures has long been recognized as a vital subject in computing and is part of the core curriculum of computer science and computer engineering undergraduate degrees. Data structures and algorithms in Python provides an introduction to data structures and algorithms, including their design, analysis, and implementation. This book is designed for use in a beginning level data structures course or in an intermediate level introduction to algorithms course. We discuss its use for such courses in more detail later in this preface. To promote the development of robust and reusable software, we have tried to take a consistent object-oriented viewpoint throughout this text. One of the main ideas of the object-oriented approach is that the data should be presented as being encapsulated with the methods that access and modify them. That is, rather than simply viewing data as a collection of bytes and addresses, we think of data objects as instances of an abstract data type, right? ADT. So let's go over that one more time. That is, rather than simply viewing data as a collection of bytes and address, we think of data objects as instances of an abstract data type, which includes a repertoire of methods for performing operations on data objects of this type. We then emphasize that there may be several different implementation strategies for a particular ADT or abstract data type, and explore the relative pros and cons of these choices. We provide complete Python implementations for almost all data structures and algorithms discussed, and we introduce important object-oriented design patterns as means to organize these implementations into reusable components. Cool. Desired outcomes for readers. They have the knowledge of the most common abstractions for data collections. Okay, they understand algorithmic strategies. They can analyze algorithmic performance. They can wisely use data structures, algorithms. They have experience working with concrete implementations. They can apply data structures and algorithms to solve complex problems. In support of the last goal, we present many example applications of data structures throughout the book, including the process of file systems, matching of tags in structured formats such as HTML, simple cryptography, text frequency analysis, automated geometric layout, Huffman coding, DNA sequence alignment, and search engine indexing. Interesting. A lot of big concepts here. Book features. This book is based upon the book Data Structures and Algorithms in Java by Goodrich and Tomasia, and the related data structures and algorithms in C++. However, this book is not simply a translation of the other books to Python. In adapting the materials for this book, we have significantly redesigned the organization and content of the book as follows. The code base has been entirely redesigned to take advantage of the features of Python, such as use of generators for iterating elements of collection. Many algorithms that were presented as pseudocode in the Java and C++ versions are directly presented as complete Python code. In general, ADTs, or abstract data type, abstract data types are defined to have consistent interface with Python's built-in data types and those in Python's collections module. In Chapter 5 provides an in-depth exploration of the dynamic array-based underpinnings of Python's built-in list, tuple, and str classes. New Appendix A serves as an additional reference. Okay. Online resources. Gotcha. Students are encouraged to use this site along with the book to help exercise and increase understanding of the subject. Instructors are likewise welcome to use the site to help plan, organize, and present their course materials. Included on this website is a collection of educational aids that augment the topics of this book for both students and instructors. Because of their added value, some of these online resources are password protected. All the Python source code are presented in this book. Okay. Content organization, cool. Prerequisite: we assume that the reader is at least vaguely familiar with a high-level programming language such as Python, and he or she understands that the main constructs from such a high-level language, including variables, decision structures, iteration structures, and functions. Okay. Check, 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 and check. All right. Let's see here. My thing wasn't set up. All right. For readers who are familiar with these concepts but not with how they are expressed in Python, we provide a primer of Python language in Chapter 1. Okay. We delayed treatment of object-oriented programming in Python until Chapter 2. This chapter is useful for those new to Python, for those who may be familiar in Python yet not with object-oriented programming. Gotcha. Even so, in Chapter 3, we discussed the 7 most important functions for algorithm analysis. In fact, sections that use something other than one of these 7 functions are considered optional and are indicated with a star. Okay. Relation to computer science curriculum. To assist instructors in designing a course, here, okay, gotcha. About the authors. Skip over this stuff. If you're interested in it, feel free to read. Acknowledgements. Alright, Chapter 1. Alright, Python primer. Building data structures and algorithms requires that we communicate detailed instructions to a computer. An excellent way to perform such communications is using a high-level computer language such as Python. Okay, this is just an overview of Python. Gotcha. Python is formally an interpreted language. Commands are executed through a piece of software known as the Python interpreter. The interpreter receives a command, evaluates that command, and reports the results of the command. While the interpreter can be used interactively, especially when debugging, a programmer typically defines a series of commands in advance and saves those commands in a plain text file known as source code or as a script. For Python, source code is conveniently stored in a file name called .py. Okay. IDEs. Preview of Python program. While loops. All not done. Okay. Objects in Python. Okay, we'll start here. Python is an object-oriented language, and classes form the basis of all data types. In this section, we describe key aspects of Python's object models, and we introduce Python's built-in classes such as the int class for integers, the float class for floating point values, and the stir class for character strings. As more thorough presentation of object-oriented focus in chapter 2. Okay. Most important of all Python commands is an assignment statement such as temperature equals. Okay, got you. This is just identifiers. Identifiers are case sensitive. Okay, these are just keywords. Okay. Once an alias. Okay. A program can establish an alias by assigning a second identifier to an existing object. Continuing with our example earlier in figure 1.2 portrays the result of subsequent assignment original equals temperature. Mm-hmm. Figure 1.2, gotcha. Once an alias has been established, either name can be used to access under the underlying object. Okay, I already know about this stuff. The bool class. Float, yes. List. Okay. Objects in Python, sequence lists, tuples, and stir classes. The list, tuple, and stir classes are sequence types in Python, representing a collection of values in which the order is significant. The list class is the most general, representing a sequence of arbitrary objects akin to an array in other languages. The tuple class is an immutable version of the list class, benefiting from a streamlined internal representation. The stir class is specifically designed for representing an immutable sequence of text characters. We note that Python does not have a separate class for characters. They are just strings with one length. Gotcha. A list instance, right? A list instance stores a sequence of objects. A list is a referential structure as it's technically stored as a sequence of references to its elements. Elements are a list of a list may be arbitrary objects, including the none object, right? Lists are array-based sequences and are zero indexed. Thus, the list of a length n has an elements from 0 to n minus 1 inclusive. Lists are perhaps the most used container type in Python, and they are extremely central to our study in data structures and algorithms. They have many valuable behaviors, including the ability to dynamically expand and contract their capacities as needed. In this chapter, we will discuss only the most basic properties of lists. We revisit the inner workings of all Python sequence types as the focus of chapter 5. Python uses the characters brackets as delimiters for the list literal, with brackets itself being an empty list. As an example, bracket red, green, blue is a list containing characters 3 string instances. The contents of a list literal need to be expressed as literals. As if identifiers A and B have been established in syntax A, B is legitimate. The list constructor produces an empty list by default. However, the constructor will accept any parameter that is an iterable type. It will be discussed iteration further in section 1.8, but examples of iterable types include all of the standard container types, strings, list, tuples, set, dictionaries. For examples, the syntax list hello produces a list of the individual characters hello, Hello. Because the existing string list is itself iterable, the syntax backup equals list data, right? What is it? Data equals hello. Syntax backup list can be used to construct a new list instance referencing the same contents as the original. Oh, yeah. Okay. 2, 3, 5, 7, 11, 13, 17. Figure 1.4. Python's internal representation is a list of integers instantiated as prime 2, 3, 5, 7, 11, 13. The implicit indices of the elements are shown each below each entry. Yeah, okay. The tuple class, all right. So we have the list right? Is a referential structure as it technically stores references to its elements. Elements in a list may be arbitrary objects, including right. So these are array based. Array based 0 right indexed. So I know we know all this already, but just trying to keep concepts solid here. Um, okay. All right, let's keep moving here. The tuple class, right? Not this class, but the tuple class. All right, so the tuple class, it provides an immutable version of a sequence, and therefore instances have an internal representation that may be more streamlined than that of a list. While Python uses the bracket characters to delimit a list, a parentheses to delimit a tuple, with parentheses being an empty tuple. There's one important subtlety. To express a tuple of length 1 as a literal, a comma must be placed after the element, but within the parentheses. For example, 17 as one element tuple. The reason for this requires that without the trailing comma, the expression 17 is viewed as a simple parenthesized numeric expression. Hey, Pankaj, how you doing? Hopefully I said your name right. Please correct me if I didn't. I'd love to be able to say it right for you and communicate with you appropriately. But I appreciate you joining and leave a comment. Just learning some data structures right now. Just doing just giving me a breakdown of just Python primer. It's about pretty basic stuff, but just wanted to go over it quickly here. And yeah, just taking some notes here. So the tuple class is a immutable version of a sequence. Uh, right. So we need to also say or brackets or list like that. Cool. This is going to be, so we'll do here, and then this is going to be parentheses x. So then we'll do like this. This is a tuple with one element requires the trailing comma. Right? Parentheses. Oh, I spelled that so. Parentheses are used to define a tuple. Parentheses, yes. All right, so an immutable version, right? So meaning that it cannot be changed. The order is matters. Oh, come on, let me just do this guy. Oh my gosh. There we go. So order matters and is consistent. Okay. All right, so so let's express. For example, 17 is one element, be parentheses. Okay, gotcha. Stir class. So let's copy this over. Stir class, right? And we'll get rid of this junk. Okay. The Python stir class is specifically designed to efficiently represent an immutable sequence of characters based upon the Unicode internal character set. Strings have a more compact internal representation than the referential lists and tuples as portrayed in Figure 1.5. A Python string, which is an indexed sequence of characters. So sample 0, 1, 2, 3, 4, 5. Gotcha. String literals can be enclosed in single quotes such as quote hello or double quotes such as quote hello. Gotcha. This choice is convenient, especially when using another quotation character, actual characters of a sequence, as don't worry. Gotcha. Alternatively, the quote delimiter can be designated using a backslash as a so-called escape character. So quote don't. Oh, gotcha. So you can escape out to. Gotcha. Don't because the backslash has its purpose. The backslash itself must be escaped to occur natural characters in the string literal. For a string that would be displayed, see Python. Oh, gotcha. So let's see this Python. Oh, because the backslash has this purpose, the backslash itself must be escaped to occur as a natural character in the string. So we had to put two of them together to get one. Other commonly escaped characters are backslash n for a new line and backslash t for tab. Unicode characters can be included, such as quote 20 backslash u20 ac for these. What was that? Sky, do you hear that? What was that? For the string 20 euros. Hey Eric, how you doing? Thanks for leaving a comment. I appreciate you joining, and feel free to follow the channel so we can stay in touch and communicate on our journeys learning Python. I'm just reading the book. I've already read Python Crash Course. part one, which is the learning, and then I have made some beginner projects in Python, such as the Task Tracker app, which I made, on stream here. And then I made my final project for Harvard CS50P, which I also took. And so you can see the Task Tracker project on GitHub right now. It's in the link in the chat right now. Not in the chat, in the description of this stream. So yeah, I've been, and then join the Discord if you feel like it. Also, that's where we communicate offline to, interact and make announcements and stuff. All right. So cool. Python also supports the delimiter triple quotes or triple quotes double quotes to begin an end string and end a string literal. The advantage of such triple string quotes is a new line character. It can be embedded naturally rather than escape. This can greatly improve the readability of long multi-line strings in source code. For example, at the beginning of the code fragment 1.1, rather than use separate print statements for each line of the introductory output, we can use a single print statement followed as print triple quotes welcome. Okay, so you can use triple quotes to just keep the string going. Interesting. Okay, so let's just jot down some notes about the stir class here. What should we say, guys? Hello to everybody in here. Thanks for joining. We got 6 people, it looks like. I appreciate everybody for stopping in this evening. Feel free to follow the channel so we can stay up to date and communicate about our Python learning and interact within the chat. Just learning about data structure and algorithms here, and just starting off with some introduction about warm-up and refresher on Python. So string class, what do we want to jot down by here? Designed to efficiently represent an immutable sequence of characters based upon the Unicode internal character set, right? Okay, and then we'll say like this, quote or single quote to our used quotes, double or single are used to define strings, right? Cool. And then gotcha. Backslash escape character to because the backslash has a purpose. Okay, gotcha. Escape character to I don't know what I'll say for that, but I'll just say that for now. Okay. So, okay, the set and frozen set classes. So Python's set class represents a mathematical notation of a set, namely a collection of elements without duplicates and without an inherent order to those elements. The major advantage of using a set as opposed to a list is that it's a highly optimized method for checking whether a specific element is contained within the set. This is based on the data structure known as a hash table, which will be a primary topic of Chapter 10. However, there are 2 important restrictions due to the algorithmic underpinnings. The first is that the set does not maintain the elements in any particular order. The second is that the only instance of immutable types can be added to a Python set. A second is that only instances of immutable types can be added to Python sets. Therefore, objects such as integers, floating point numbers, and character strings are eligible to be elements in a set. It is possible to maintain a set of tuples, but not a set of lists or a set of sets. Set of lists or set of sets. A list and sets are lists and sets are mutable, right? The frozen set class is an immutable form of the set, so it's legal to have a set of frozen sets. Python uses curly braces and as delimiters for the set. For example, curly brace 17 or curly braces red, blue, green. The exception is for this rule is that curly braces does not represent an empty set. For historical reasons, it represents an empty dictionary. Instead, the constructor syntax set produces an empty set. If an iterable parameter is set to the constructor, if an iterable parameter is sent to the constructor, then the set of distinct elements is produced. For example, set hello produces HELO and removes one L. Gotcha. Interesting. So the set class is unique elements only and in no particular order. Pretty easy. Set class. All right, hello to the people that are here. Appreciate you joining me tonight. I'm just studying up on just starting this book here, Data Structures and Algorithms in Python, by Michael Goodrich and Tomasia and Goldwasser. Alright, I think this book is used in some college courses, so if you're using this book in college, maybe this could be a resource to you for getting some extra studying in. Alright, let's go ahead and continue on with the set class here. So the set class represents a mathematical notation of a set, namely a collection of elements without duplication. Elements, a collection of elements without duplicates, right? And without an inherent order to those elements. Only instances of immutable types. Only immutable instances types can be made sets. Right, so things that can't be changed. Therefore, objects such as integers, floating point numbers, characters, or strings are eligible. Cool. Immutable instances types can be made. Therefore, objects such as, right, this is objects such as integers, floats, and characters, strings. Mute. It is possible to maintain a set of tuples, but not a set of lists. So a tuple, right, was a immutable version of a sequence, no matter what kind. And then So a tuple is just the order matters, but you can have any amount of characters you want, and you can have duplicates. A set is order doesn't matter, but you only can have unique elements, right? So lists are not mutable in types. Lists cannot be made into sets, right? A frozen set class, right, is mutable form of the set type. Frozen set class, immutable form of the set type. Okay, so then we'll say curly braces with an element inside. Are used. Curly brackets are used to define a set, but an empty with an right, with data inside. Empty set is right. Set is used to make an empty set. Perfect. All right, so the set is used to make an empty set because that makes a dictionary. Great. The dictionary class. The Python's dicts class represents dictionary or mapping from a set of key to associated values. For example, dictionary map from unique student ID numbers to a large student record. Python implements a dict using almost identical approach to that of a set, but with storage of associated values. The dictionary literal uses curly braces because dictionaries were introduced in Python prior to sets. The literal form curly braces produce an empty dictionary. A non-empty dictionary is expressed using a comma-separated series of key values, pairs. For example, dictionary ja Irish, de German maps ga to Irish and de to German. The constructor for the dict class accepts an existing map as a parameter, in which it creates a new dictionary with identical associations as the existing one. Alternatively, the constructor accepts a sequence of key value pairs as a parameter, as in dict pairs with pairs equals that and that. Okay. So you can give it to tuples, right? Within a set, within a list, and that'll create a dictionary if you just dict it. Use the dict function. Right, key value inside of a tuple, which can go inside of a list. Interesting. Okay. So just trying to keep, obviously we know we've worked with lists before, we've worked with strings, we've worked with dictionaries, but it's trying to keep all their unique features, sets and tuples added in there now, and trying to keep those features differentiated is the hard part. So a list is just a sequence of elements and structure, right, that is iterable, can have none in it. A tuple is defined with parentheses, and it's a list of elements where the order matters, but you can have as many repeats of them as you want. It's a list, but with order that matters. A stir is like a immutable list, or a tuple, I guess, of characters, and then a tuple of characters, and then a set uh, is a collection of elements without duplicates, so of unique elements without duplicates, right? So a set is unique elements. So is there a way to remember this? Set unique elements. SET. I don't know. Okay. So then the dict class, right? Let's just do this quick. We know the dict class already. We're already familiar with that. All right. Hello to those that are in here. Thank you for joining. Feel free to follow along so you can stay up to date and learn along with me as I stream my self-teaching journey of Python, and now I'm diving into some deeper topics here of data structures and algorithms. All right. The dictionary class represents a dictionary or mapping from a set of distinct keys, value pairs, right? Okay, so yeah, that's all I'll say for that. Right, I'll just really quickly actually add in that it's or dict, right, are used to create or to define a dictionary. Cool. Moving on here, expression, operators, and precedents. In the previous section, we demonstrated how names can be used to identify existing objects and how literals and constructors can be used to create instances of built-in classes. Existing values can be combined into larger syntactic expressions using a variety of special symbols and keywords known as operators. Yeah, the semantics of an operator depend upon the type of its operands. For example, when A and B are numbers, the syntax A plus B indicates the addition, while if A and B are strings, the operator indicates concatenation. In this section, we describe Python's operators in various contexts, but in the built-in types. We continue in section 1.3.1 by discussing compound expressions, such as A plus B times C, which rely on the evaluation of two more operators. The order in which operations of a compound expression are evaluated can affect the overall value of the expression. For this reason, Python defines a specific order of the precedence for evaluating operators, and it allows a programmer to override this order by using explicit parentheses to group sub-expressions. Yeah, just like using PEMDAS and any normal kind of calculator, I guess. Not that difficult here. Pretty easy and straightforward. Logical operators. Python supports the following operators in Boolean values: and, not, and or. The and or operators short circuit in that they do not evaluate the second operand if the result can be determined based on the value of the first operand. This feature is useful when constructing Boolean expressions in which the first test, that is, a certain condition, such as a reference not being none, and then the test, a condition that could have otherwise generated an error condition, had the test not succeeded. Equality operators. Python supports the following operators to test two notions of equality: is, same identity; is not, different identity; equals, equivalent; not equals, not equivalent, right? Expression A is B evaluates true precisely when identifiers A and B are aliases um, for the same object. The expression A is equal to B tests a more general notion of equivalence. If identifiers A and B are referred to the same object, then A is equal to B should evaluate to true, yet A is equal to B evaluates to true. When the identifier refers Yet A is equal to B also evaluates to true when the identifier refers to different objects that happen to have values that are deemed equivalent. The precise notation of equivalence depends on the data type. For example, two strings can be considered equivalent if they match character for character. Two sets are equivalent if they have the same contents, irrespective of order. In most programming situations, the equivalence test is equal to and is not equal to are the appropriate operators. Use of is and is not should be reserved for a situation in which it is necessary to detect true aliasing. It's like is in this list, right? Data types may define a natural order via the following operators: less than, equal to, greater than equal to. Yeah, this is basic stuff. We know this. These operators have expected behaviors for numerical types and define lexicographically and case sensitively for strings. An exception is raised if operands have different types, incompatible types. Arithmetic operators: addition, subtraction, multiplication, true division, integer division, modulo operator. The use of addition and subtraction and multiplication is straightforward, noting if that both operands have type int, then the result is an int as well. If one or both operands have type float, then the result will be a float. Python takes more care in this treatment of division. We first consider the case in which both operands have type int. For example, 27 divided by 4. Austin says, nice 69 subs, bro. Hey, thank you so much to everybody out there. 69 subs. It's a huge jump. I was just streaming one night about 2 weeks ago, and my view count just went up out of nowhere. I had no one in my streams ever, and that one night I ended up with like 300 people at the end that a total had stopped in, and it really just overnight kind of changed the trajectory of my channel. And it's not meant for growth and anything. It's meant for my learning and for me to document and to be a reference for myself. But if other people are following along, then that's great as well. But Austin, thanks so much for subbing along if you were number 69. All right. Python, we'll first consider the case in which both operands have the type int. For example, the quantity 27 divided by 4. In mathematical notation, 27 divided by 4 equals 6 3/4, or 6.75. In Python, the division operator designates true division, returning the floating point value results of the computation. Thus, 27 divided by 4 is float 6.75. Python supports the pair of operators divide, and modulo to perform the integral calculations. The expression 27, I'm not sure what this is supposed to, what is this called? I know this is integer. Integer divided by 4 evaluates to int value 6. Is it just, it's how many times it can be divided in a whole? Okay. That's interesting. Thank you, Austin, for the kind words. That's really sweet of you, and thanks for stopping in this evening. I really appreciate it. And please, tell me where you're at in your coding learning. Are you experienced? Are you new? Are you just what's going on? How are you doing? All right. So it just this integer division returns the whole numbers that can go into a operation, right? Division operation. So this returns the whole value, whereas the modulo returns the remainder. Int value 6, the mathematical floor for the quotient. And expression 27 modulo 4 evaluates to int value 3, the remainder of the integral division, because there was a remainder of 3 out of 4 to be created a whole number, right? Hey, Doll, thanks for joining. Appreciate you leaving a comment and joining me tonight. Super nice of you. All right. We know that languages such as C, C++, and Java do not support the dash division, integer division operator, and instead the dash operator returns the truncated quotient when both operands have an integral type, and the result of true division when at least one operand has a floating point type. Python carefully extends the semantics of dash dash and modulo to cases where one or both operands are negative. For the sake of notation, let us assume that the variables of n and m represent respectively the dividend and divisor of the quotient n over m, right? And what q is equal to n divided by m, and r is equal to n modulo m. Python guarantees that q times n plus r equals n. Okay, where are we going here? Why did we just all of a sudden just ramp up to something wild? Okay, Python carefully extends the semantics of the integer division and the modulo division to cases where one or both operands are negative. For the sake of notation, let's assume that the variables n and m represent respectively the dividend and the divisor of a quotient, right? And that q is equal to n. Q is equal to the amount of whole values that can be associated in this, right? The integers, whole integers returned, and then r is equal to the remainder. Python guarantees that the amount of whole values times the divisor plus the remainder will equal to the dividend, okay? We already saw that in an example of this identity with positive operands, as 6 times 4 plus 3 is equal to 27. Okay, so you're just adding everything back up to get to where you were, right? You do 6 times 4 plus the remainder is equal to the 27. When the divisor m is positive, right, when you're dividing by a positive number, Python further guarantees that 0 is greater than the remainder, which is greater to m, right? Yeah, because you're dividing by a whole number, or a positive number, so you're going to get a remainder value that's either less than that or but greater than 0 or equal to. As a consequence, we find that negative 27 integer divided by 4, right? So this would be, you can get 6 out of here equivalent to negative 7. And, because you can get a whole 4, you go 4, back down 4, back to negative 4, negative 8. Yeah, so yeah. Okay. And negative 27 modulo 4 evaluates to 1. As negative 7 times 4 plus 1 is equal to negative 27. When the divisor is negative, Python guarantees that m is less than the remainder, which is less than or equal to 0. As an example, 27 integer division negative 4 is negative 7. Jesus Christ. The conventions for the integer division and the modulo operators are even extended to floating point operands. The expression q is equal to n um, divided by m means that the integral floor of the quotient is uh, being that the integral floor of the quotient and the remainder is equal to n modulo m, being that the remainder to ensure that q, okay, gotcha. Okay, this is all just kind of fluff. If you got lost in this, don't worry. I think this is kind of, they poorly explain this, or I'm just dumb. Probably that. Okay, bitwise operators. All right, Python provides the following bitwise operators for integers: bitwise complement, and bitwise or, bitwise exclusive, shift bits left filling in with zero, shift bits right filling in with the sign bit. Sequence operators. Each of Python's built-in sequence types, string, tuple, and list, support the following operator syntaxes. Yeah, elements. Okay, slices. Right, we know slices. Kitty, stop scratching the wall. Hey, chicken, thanks for joining. Good to see you again. This is data structures and algorithms in Python. Right, so you can index into a list or a str or a tuple. You can create a slice from start to stop. You can create a slice with a skip. Right, at what skip steps would you like to do? But not equaling or stop. Okay, concatenation of sequences, string, shorthand for s plus s plus s k times. Okay, containment check, value in, value not in. Yep. Python relies on zero indexing of sequences, thus a sequence of length n has elements indexed from 0 to n minus 1 inclusive. Python also supports the use of negative indices, which denote a distance from the end of the sequence. Index -1 denotes the last element, -2 the second to last, and so on. Python uses a slicing notation to describe a sequence of sequences. Slices are described as half-opened intervals with a start index that is included and a stop index that is excluded. For example, the syntax 3 to 8, data 3 8 denotes a subsequence including the 5 indices 3, 4, 5, 6, and 7, right? Because 8's not included in a slice. The finish. Stop at 8, right? Don't add 8. You stop at 8 up to 8. What do you mean by that, chicken? Data science in Python? I'm not sure what you mean by that. It's pretty broad. You have a more, like, course or book or something? This is kind of getting in there, like data structures and algorithms. Like, this is kind of getting into that realm. Oh, I hate how it glitches like this with the second monitor. Sorry, let me get my screen back here. There it is. Come on. Ugh. Why? Okay, this is annoying. Come on. Okay. Okay, come on. There we go. Sorry, guys. All right. An optional step value, positive or negative, can be indicated as a third parameter of a slice. If a start-stop index is omitted, then the slicing notation it is presumed to designate a respective extreme of the original sequence. Because the lists are mutable, the syntax sj equals value can be used to replace an element at a given index. Lists also support a syntax del that removes the designated element from that list. Slice notation can be used to replace or delete a sublist. The notion val in S can be used for any of the sequences to see if there is an element equivalent to val in the sequence. For strings, the syntax can be used to check for a single character or for a larger substring. As with amp and example, all sequences define comparisons operations based on lexicographic order, performing an element by element comparison until the first element is found. For example, 569 is less than 57 um, because of the entries at index 1. Therefore, you follow because the entries at index 1. Therefore, you follow the following operations are supported by sequence types. Okay, gotcha. Sets and frozen sets support the following operators. Key in S, key not in S, key S1 is equivalent, S1 is not equivalent. S2, the intersection, the union. Okay, so you can do unions and intersections too. Note well that sets do not guarantee a particular order of their elements, so the comparison operators such as less than are not lexicographic, rather they are based on the mathematical notation of a subset. As a result, the comparison operators define a partial order but not a total order. As disjoint sets are neither less than, equal to, or greater than each other, sets also support many fundamental behaviors through named methods. Add, remove. We'll explore their functionality more in Chapter 10. Dictionaries, like sets, do not maintain a well-defined order on their elements. Furthermore, the concept of a subset is not typically meaningful for dictionaries, so the dict class does not support operators such as less than. Dictionaries support the notion of equivalences. With D1 is equal to D2, if the two dictionaries contain the same set of key value pairs, the most widely used behavior of dictionaries is accessing a value associated with a particular key, with the indexing sequence D of key, right? D at index K. The supported operators are the following. Associated value with a given key, gotcha, del, not in, is equal to, not equal to. Dictionaries also support many useful behaviors. Okay. Alright. Extended assignment operators. Python supports an extended assignment operator for most binary operations. For example, the following syntax such as count plus is equal to 5. By default, this is shorthand. The more verbose count is equal to count plus 5. Okay, yeah. But for immutable types such as number or strings, one should not presume that the syntax changes the value of the existing object, but instead that it will reassign the identifier as a newly constructed value. The discussion of figure 1.3. See discussion of figure 1.3. However, it is possible for a type to be redefined, such as semantic, to mutable object. However, it is possible for a type to redefine such semantics to mutable objects, as the list class does for the plus equals operator. So alpha is equal to 1, 2, 3, a list with 1, 2, 3. Beta is equal to alpha, so beta is equal to the alpha list. Beta plus 4, 5, 6. Beta is equal to beta plus 5, 6, 7. Print alpha. Well, you'll just, alpha is 1, 2, 3, right? Beta is equal to alpha. Beta plus 1, 2, 4, 5, 4, 5. So an alias for alpha is beta. So everything, okay, so if you do something, if you make an alias for it, right, you set it equal to another variable, and then you do something to that alias, it also does it to the, right, to whatever the other alias is. But then if you reassign beta to a new list, plus 5, 6, plus 6 and 7, gotcha. All right, this example demonstrates the subtle differences between list semantics for the syntax beta plus equals foo versus beta plus equals foo. Yeah. All right, so this has kind of been a lot of just review, um, getting you right. So compound expression, programming languages must have clear rules for the order in which compound expressions such as 5 plus 2 times 3 are evaluated. The formal order of precedence for operators in Python is given in table 1.3. Operators in a category with higher precedence will be evaluated before those with lower precedence unless the expression is otherwise parenthesized. Therefore, we see that Python gives precedence. Okay, so this is just a precedent. Python allows a chained assignment, says x equals to y, which is equals to 0, to assign multiple identifiers to the rightmost value. Python also allows the chaining of comparison operators. For example, the expression 1 is less than or equal to x plus y, which is less than or equal to 10, is evaluated for the compound. 1 is equal to, okay, but without computing the intermediate values x plus y twice. Okay. Straightforward. Control flow. We're moving on here. Hey DJ Batman, how you doing? Thanks for joining and leaving a comment. Appreciate you coming in here, man. In this section, we reviewed Python's most fundamental control sources, loops. Gotcha. Okay, I'm gonna pretty fast through this because I know a lot of it already. So, if statements, right? Okay, gotcha. Might have if doors close, open door, and then advance. Notice that the final comment advance is not indented, therefore not a part of the conditional body. Um, it will be executed unconditionally, although after opening a closed door. So you're going to advance if there's a closed door. You're going to open it in advance no matter what. Okay, gotcha. We may nest one control structure within another, relying on indentation to make clear the extent of various bodies. If doors closed, if doors locked, unlock door, then open the door, then advance, right? Yeah, okay. The logic explained here. So doors closed, true. Doors locked, true. Unlock door, right? If doors closed, well, that statement's false. Well, we advance, right? It's open. It's closed. Well, is it locked? Yes. Unlock the door. Is it locked? No. We'll open the door. Okay, gotcha. Cool. DJ Batman, I'm just reading data structures and algorithms in Python. Shoot, did this again. No. Oh my God. This glitch with the Mac OS has got to fix this. It is so brutal. Yeah, sorry, Batman. I'm reading DJ data data structures and algorithms in Python. Just going over the Python primer in chapter 1. We just started the book. That'd be a great time to step in. Feel free to follow the channel to stay up to date with our learning and learn along with us. That's the whole point of this. All right, loops, while loop. Okay, gotcha. I do want to read this part though, because there are more parts about loops that I want to know. As with an if statement, condition can be an arbitrary Boolean expression, and body can be an arbitrary block of code representing nested control structures. The execution of a while loop begins with the test of the Boolean condition. If the condition evaluates to true, the body of the loop is performed. After each execution, the loop condition is retested. If it evaluates to true, another iteration of the body is performed. When the conditional test evaluates to false, assuming it ever does, the loop is exited. While the flow of control continues just beyond the body of the loop. As an example, here is a loop that advances an index through a sequence of characters while finding an entry value x or reaching the end sequence. So j is equal to 0. So while j is less than the length of data, so whatever data is, and data So while j is less than the length of data, j is 0, so it is the less than length of data. So it's going to go up to it's going to loop through every one of the data points, and data at index j, okay, data at that point does not equal the value x, we're going to move on. So you're going to just start from the beginning of the list and go in if that is, gotcha. While you're, okay, so let me try to explain this. I'm stuttering all over the place. Sorry, guys. But so j is equal to 0, while j is less than the length of the list. So because we're starting at 0, if the list is 1, we're only going to do it once. If the list is twice, we're going to do it twice, so on and so forth. And the point we're at does not equal x, right? If that index point we're at, if it is, then we're going to move. We're going to move on and check. We're checking to see, I guess, probably where x is. The length function, which we introduced in section 1.5.2, returns the length of a sequence such as a string, a list, or a string. The correctness of this loop relies on the short circuiting behavior and of the AND operator, as described on page 12. We intentionally test j is less than the length of data to ensure that j is a valid index. Prior to accessing element data j, had we written the compound condition with the opposite order that evaluates data j would eventually raise an index error when x is not found. See section 1.7 for discussion of exceptions. As written, when the loop terminates, variable j's value will be the index at the of the leftmost occurrence of x. Yeah, we're going to find the first occurrence of x, and that'll be represented in the value of j. If found, or otherwise the length of the sequence, which is recognizable as an invalid index to indicate further failure of the search. It is worth noting that the code behaves correctly even in the special case when the list is empty, as the condition j is less than the length of data, which will initially fail, and the body of the loop will never be executed, right? So if the list is 0, well, it's not less than or equal to it. So j can't be negative in this case because you can't move on. So it'll never continue because j is 0. Perfect. Yeah, so we talked about some dictionaries earlier. This is just refresher though. Just kind of moving through this pretty quick, as we already have some experience with Python. Feel free to check out the Task Tracker Python project we made on stream here over the past few weeks. It's in the description of this stream. It's on my GitHub. You can clone the repo and use the Task Tracker app. It orders your tasks for you based on priority and due dates, and tracks them by time, and tasks can expire. It's really quite neat and cool. And then feel free to follow along to the channel so we can communicate and stay in touch and learn together. All right. Cool. For loops. Gotcha. Python's for loop syntax is a more convenient alternative to while loop. Gotcha. Cool. For element in iterable body. Cool. This is easy. I know for loops pretty well. A second classic example we consider finding. Okay. So biggest equals data index as 0. We assumed a non-empty list. For value in data. If value is greater than biggest equals the value, right? Although we could accomplish both of these above tasks with a while loop, the for, okay, let's go back and read this. Screw it. As an instructive example of such a loop, we consider a task of computing the sum of the list of numbers. Admittedly, Python has a built-in function, sum, for this purpose, but we'll perform this calculation with the loop, assuming the data identifies as a list. Okay, total equals 0 for the value in the data set. Total equals plus minus equals value, right? So for every point, you're just going to add on every point in the data list and get a total sum. The loop does that, got you. As a second classic example, we consider the task of finding the maximum value in a list of elements. Again, admitting that Python's built-in max functionality provides the support, okay? We can assume that the list data has at least one element, right? We can implement this task as follows. So as we assume non-empty list, so biggest would be the data point at the zero index, because if it's data at zero index, if the list was empty, that would be the biggest value, or not empty. If the data list had one value in it, meaning at index point zero, that would be the biggest value, just by default. So for value in data in the data set, if the value is greater than the biggest, we're going to set that value to the biggest variable. Although we could accomplish both of these above tasks with a while loop, the for loop syntax had an advantage of simplicity, as there is no need to manage an explicit index into the list, nor to author a Boolean loop condition. Furthermore, we can use a for loop in cases which a while loop does not apply, such as when iterating through a collection, such as a set, that does not support any direct form of indexing. Thank you for the sub, DJ Batman. I appreciate it. I look forward to communicating with you and working with you, and learning. Index-based for loops. Okay, so the simplicity of a standard for loop over the element of a list is wonderful. However, one limitation of that form is that we do not know where an element resides within the sequence. In some applications, we need knowledge of the index at an element of the sequence. For example, suppose that we want to know where the maximum element in a list resides. Rather than directly looping over the elements of the list in that case, we prefer to loop over all the possible indices of the list. For example, suppose we want to know where the maximum element in a list resides. Okay, rather than looping through over every element in the list, we prefer to loop over all the possible indices of the list. For this purpose, Python provides a built-in class named range. Yep. That generates integer sequences. We will discuss generators. Okay. In the simplest form, the syntax range n generates the series of n values 0 to n minus 1 conveniently. These are precisely the series of valid indices into a sequence of length n. Therefore, a standard Python idiom for the looping through the series of indices. A data sequence uses a syntax. Therefore, okay, for j in range of length of data, right? In this case, identifier j is not an element of the data. It is an integer. But the expression data j can be used to retrieve the respective element. For example, we can find the index of the maximum element of a list as follows. So big index is equal to 0. For j in the range of for element data points for the range, the length of the list. If data j is less than data big index equal to j. Okay, let's break this down here. In this case, so big index is equal to 0. For j in range, the length of data from 0 to for the range of the list, if data of index j, so we're if data at that index j is less than data big index, or is greater than data of big index, we're going to assign big index to j. Okay, so basically you're wanting to get the index of the largest value within the data list. So you set the big index to equal to 0 to just, initialize the variable if there is none. If there is only one element in the list, right? That would be the index 0. For j is just an integer, so for every integer in the range of a length of our list, right? What this basically means is that you have the length of your list, so which provides a single value back. So if our data value set is 5 integers, 1, 2, 3, 4, 5, our length would return 5. Data would be 5. Well, our range would give us 0 to 5, right? 0, 1, 2, 3, and 4, which would be 5 values. So that it just takes our length and provides a range from 0 to that length. So for every integer in the range of 0 to the end of our list value, so 0 to 5 in this case that I made up, if the value, right, if the data point at that index point, j, is greater than this value here, data of big index, right, of the, if the, if it's bigger than the very first value in the list of data, then we're going to assign it, right? So they're just assuming this whole big index 0, I think, is what's throwing me off and everything. They're just assuming that it's like a safety net. If the list only has one element, then that is the big index, right? So if it has more than one, right? If there's more than one, we're going to go and loop through all of those and determine if it's bigger than that big index value. If it is, if that's bigger, then we're going to override that index value and save it as j. Big index is j now. Okay, gotcha. Break and continue statements. Python supports a break statement that immediately terminates a while or for loop when executed within its body. More formally, if applied within a nested control structure. Okay, I know about break and continues. Functions. In this section, we explore the creations of functions. In Python, as we did in this section in 1.2.2, we draw a distinction between functions and methods. We use the general term function to describe a traditional stateless function that is invoked without the context of a particular class or an instance of that class, such as sorted data. We use the more specific term method to describe a member function that is invoked upon a specific object using an object-oriented message passing syntax, such as data.sort. In this section, we only consider pure functions. Methods will be explored in more general object-oriented principles in Chapter 2. Cool. We begin with an example to demonstrate the syntax for defining functions in Python. The following function counts the number of occurrences of a given target value within any form of an iterable data set. So def count with a parameter of data and target. We're given a default value of n equals 0 for item in data. If item is equal to the target value provided, we're going to increase n by 1. And then so you're going to count how many times you found the target value and return that value. The first line beginning with the keyword def serves as the function's signature. This establishes a new identifier as the name of the function, count. In this example, and it establishes the number of parameters that is expected, as well as the names identifying those parameters, data and target in this example. Unlike Java and C++, Python is a dynamically typed language, and therefore a Python signature does not designate the types of those parameters, nor the type, if any, of a return value. Those expectations should be stated in the function's documentation, see section 2.2.3, and can be enforced within the body of the function, but misuse of a function will only be detected at a runtime. The remainder of the function, no, the body, gotcha. As in this case, controls the phone. Got you. Python creates a dedicated aviation record that stores information relevant to the current call. This aviation record, currently known as the namespace, to manage all identifiers as local scope within the current call. The namespace includes the function's parameters and all the other identifiers that are defined locally within the body of the function. An identifier in the local scope of the function caller has no relation to any identifier with the same name of the caller's scope, although identifiers in different scopes may be aliases to the same object. In our first example, the identifier n has a scope that is local to the function call, as it is not as does the identifier item, right? It's only local within this function. N is established here, right? In our first example, gotcha. Return. A return statement is used in the body of a function to indicate that a function should immediately cease execution at that, and that an expressed value should be returned to the caller. If a return statement is executed without an explicit argument, the none value is automatically returned. Likewise, none can be returned if the flow of control ever reaches the end of a function body without having executed a return statement. Often, a return statement will be the final command within the body of the function, as was the case in our earlier example of a count function. However, there can be multiple return statements in the same function, with conditional logic controlling such a. Okay, gotcha. So if you want, you return this true if you get this. You can return false if you get the other one. Information passing. To be a successful programmer, one must have a clear understanding of the mechanisms in which a programming language passes information to and from a function. In the context of a function signature, the identifier used to describe the expected parameters known as the formal parameters, and the objects sent to the caller when invoking the function are called the actual parameters. Parameter passing in Python follows the semantics of the standard assignment statement. When a function is invoked, each identifier that serves as a formal parameter is assigned in the function's local scope to the respective actual parameter that's provided by the caller. It's just basically saying that you have these parameters that are defined locally within the function, and the user then overlays their data within these variables, and then it corresponds to that data and runs the function. For example, consider the following call to our current function on page 23. Prizes equals count grades A, right? So it's going to count all the A's found in grades. Just before the function body is executed, the actual parameters grades and A are implicitly assigned to the formal parameters data and target as follows. Yep. These assignment statements establish identifier data as an alias for grades and target as a name for the literal A. Okay, cool. A portrayal of parameter passing in Python for the function call count grades A. Identifier data and target are formal parameters defined within the local scope of the count function. Yep. All right. The communication of a return value from the function back to the caller is similarly implemented as an assignment. Therefore, when with our sample invocation of prizes equals count grades A, the identifier prizes in the caller scope is assigned to the object that is identified as n in the return statement within our body function. So it's just saying that because we're returning a value right here, we're in our def target count, we're returning a value n, and because we are essentially this gets replaced with what's returned n, and we're assigning it to prizes. So you can assign the return value to a variable just in one line. To and function objects are not copied. This ensures that the invocation of the function is efficient. Cool. Mutable parameters. Python's parameter passing model has an additional implications when a parameter is a mutable object. Because of the formal parameter is an alias of the actual parameter, the body of the function may interact with the object in a way that changes its state. Considering again a sample invocation of the count function, if the body of the function executes the command data append f, the new entry is added to the end of the list identified as data within the function, which is one of the same. Okay, hold on. Jace, hello. Thanks for joining, dude. Appreciate you coming in. Just reading just started this new book, Data Structures and Algorithms in Python. We're on page 47 of 770 here, so a long way to go, but page 47 on day one, that's not that bad. We're 26 pages here within the guts of stuff, actually, so pretty good moves made here for just kind of, but obviously this is the easy part. The review of Python, but this is all familiar. We're just going through this for review. Considering again our sample invocation of the count function, if the body of the function executes the command data.append f, quote f, the new entry is added to the end of the list identified as data within the function, which is one and the same the list known as the caller as grades. As an aside, we note that reassigning a new value to a formal parameter with a function body, such as setting data equal to an empty list, does not alter the actual parameter, such as reassignment, simply breaks the alias. We're kind of just rambling here, I feel like. A hypothetical example of a count method that appends a new element to a list lacks common sense. There's no reason to expect such behavior, and it would be quite a poor design to have such an expected effect on parameter. There are, however, many legitimate cases in which a function may be designed and clearly documented to modify the case of a parameter. As a concrete example, we present the following implementation of a method named scale. Its primary purpose is to multiply all of the entries of a numerical data set by a given factor. Right, so def scale, it takes in two parameters, data and factor. For j in range from the length of data, so data is given as a list, apparently, in this case. So for whatever data index value j is multiplied equal to the factor. Multiply all entries of numerical data set by its factor. Interesting. Default parameter values. Python provides means for functions to support more than one possible calling signature, such a function is called a polymorphic, which is Greek for many forms. Many notable functions can be declared one or more default values for a parameter, thereby allowing the caller to invoke a function with varying numbers of actual parameters. As an artificial example, if the function is declared with the signature a, b equals 15, c equals 27, there are three parameters, the last two of which offer default values. A caller is welcome to send three actual parameters, as in foo 412.8, in which case the default values are not used. If, on the other hand, the caller only sends one parameter, foo4, the function will execute the parameter with a value of a equals 4, b 15, c 27. If a caller sends two parameters, they are assumed to be the first two, with the third being the default. Thus, foo 820 executes a8, b 20, c 27. However, if it is illegal to define a function without a signature such as bar a b equals 15 c, with b having a default value, yet not the subsequent c. If a default parameter value is present for one parameter, it must be present for all further parameters. So it has to be at the end. As a more motivating example for the use of default parameter, we revisit the task of computing a student's GPA. Rather than assume direct input and output of the console, we prefer the design of a function that computes and returns a GPA. Our original implementation uses a function mapping from each letter grade, such as B minus, to a corresponding point value, such as 2.67. While the point value system is somewhat common, it may not agree with the system used by all schools. For example, some may get assigned an A plus grade value higher than a 4.0. Therefore, we design a compute GPA function given in code fragment 1.2, which allows the caller to specify a custom mapping from grades to values, while offering the standard point system as default. So def compute grades. So grades, it takes in a parameter grades, and here it has a points default parameter, which is a dictionary of key value pairs for the letter grade corresponding to the grade point value. Okay. Number of courses equals 0. Total points equals 0. For G in grades, so um, for every grade in grade, if the grade is in points, right? Okay, so for every grade in your grades list, right? If your grades matches one of these keys in the points dictionary, um, you're going to increase the point course value by 1, right? Because you completed a course, and then you're going to add to your total points variable your points um, at index value G. So G will represent the key, right? So, oh, we're going to search through. Oh, we found he got a B plus in math. Okay, so let's go find what the grade point average would be. Oh, nope, nope, nope. Oh, there it is. So at this index point, we're going to add in the corresponding key value. Okay, it's 3.33. So total points would be added to there. Gotcha. And then return total points divided by number of courses. A function that computes a student's GPA with a point value system can be customized as an optional parameter. Cool. As an additional example of an interesting polymorphic function, we consider Python's support for range. Technically, this is a constructor for the range class, but for the sake of this discussion, we can treat it as a pure function. 3 calling syntaxes are supported. The one parameter form range n generates a sequence of integers from 0 up to, but not including n. A 2 parameter form range start stop generates integers from start up to, but not including stop. A 3 parameter range start stop step it generates a similar range as range start stop, but with increments of size step rather than 1. This combination of forms seems to violate the rules for default parameters, in particular when a single parameter is sent. When a single parameter is sent, as in range n, it serves as the stop value, which is the second parameter. The value of the start is effectively 0 in that case. However, this effect can be achieved with some sleight of hand as follows. So you can give it a start value by default, but then you can override the stop with stop none and then step 1. So you can start at 0. If stop is none, then stop equals start. Yada, yada, yada. From a technical perspective, when range n is invoked, the actual parameter n will be assigned to a formal parameter start within the body. If only one parameter is received, the start and stop values are reassigned to provide. From a technical perspective, when range n is invoked, the actual parameter will be assigned to a formal parameter start. Yeah. Within the body, if only one parameter is received, right, if stop is none, then set the stop value to equal start. And yeah, it can go on. Got you. Keyword parameters. The traditional mechanism for matching the actual parameters sent by a caller to the formal parameters declared by the function signatures based on the concept of positional arguments. For example, with the signature foo a equals 10, b 20, c equals 30, parameters sent by the caller are matched in the given order for the formal parameters. An invocation of foo5 indicates that a equals 5 while b and c are assigned to their default values. Python supports an alternative mechanism for sending parameters to a function known as keyword arguments. A keyword argument is specified by explicitly assigning an actual parameter to the form by name. For example, with the above definition of function foo, call foo c equals 5 will invoke the function with the parameter a equals 20, b equals 20, a equals 10, b equals 20, c equals 5. So just you can directly override with the keyword argument. A function's author can require that certain parameters be sent only through the keyword argument syntax. We never place a restriction in our own function's definition, but we see several important uses of keyword-only parameters in Python standard libraries. As an example, the built-in max function accepts keyword parameter, coincidentally named key, that can be used to vary the notion of maximum that is used. By default, max operates based on the natural order of elements according to the less than operator for that type. But the maximum can be computed by comparing some other aspect of elements. That is done by providing an auxiliary function that converts an natural element to some other value for the sake of comparison. For example, if we are interested in finding numerical value with magnitude that is maximal, considering negative 35 to be larger than plus 20, we can use the calling syntax max AB key equals ABS. In this case, the built-in ABS function is itself sent as the value associated with the keyword parameter key. Functions are first-class objects in Python. When max is called in this way, it will compare ABS absolute A to absolute B rather than A to B, so absolute value. The most motivation for the keyword syntax as an alternative to positional arguments is important in the case of max. The function is polymorphic in the number of arguments, allowing it to call such max A, B, C, D, therefore allowing a call such as max A, B, C, D. Therefore, it is not possible to designate a key function as a traditional positional element. Sorting functions in Python also support a similar key parameter for indicating a non-standard order. We explore it further in 9.4. Okay. Okay. Python's built-in functions, input, output, encoding, math, ordering, collections. Okay. Input, output. I'm going to skip here, skip this. Files. Open, we know open default on R mode. Read lines. Reading from a file. Exception handling. We know all of these. Exceptions. Yes, exception handling. Catching an exception. Exception handling. Pass. Iterators and generators. Page 39. In this section 1.4.2, we introduce the for loop syntax beginning as for element in iterable. And we notice that there are many types of objects in Python that qualify as being iterable. Basic container types such as lists, tuples, and sets qualify as iterable types. Furthermore, a string can be produced in an iteration of its characters, and a dictionary can produce its iteration of its keys, and a file can produce an iteration of its lines. User-defined types can also support iteration. In Python, the mechanism for iteration is based upon the following conventions. An iterator is an object that manages an iteration through a series of values. If variable I identifies as an iterable object, then each call to the built-in function next I produces a subsequent element from the underlying series with a stop iteration exception raised to indicate that there are no further elements. An iterable is an object obj that produces an iter via the syntax iterobj. Iterable. By these definitions, an instance of the list is an iterable, but not itself an iterator. While data equals 1, 2, 3, 1, 2, 4, 8 is not legal to call next data. However, an iterator object can be produced I equals iter data, and then each subsequent call next I will return an element of that list. The for loop syntax in Python simply automates this process, creating Okay, yeah. More generally, it is possible to create multiple iterators based on the same iterable object, with each iterator maintaining its own state of progress. However, uh, iterators typically maintain their state with direct reference back to the original collection of elements. For example, calling iter data on list instances produces an instance of the iter class. Okay, this kind of seems like FUD. And kind of know we know the for loops. We're good. We've gotten to it already. Generators. Okay. So when do we get out of the Python syntax here? Come on. Okay, so we have some reinforcement exercises here and chapter notes. Okay, cool. Wow. Okay, cool. So I think I will start next time. Next stream off, we will start with these exercises. I think it'll be a great way for us to break down. Write a short Python function is multiple n m that takes two integer values and returns true if n is a multiple of n and if n is equal to mi for some integer I and false otherwise. Cool. All right, guys. Thanks so much for sticking with me. Yeah, just was a really good refresher on the fundamentals of Python. Now that we've been working on projects and stuff, we've kind of forgotten about some of the basic functions and things like that that Python can provide. So this was a great refresher on those, and just on the more formalities of what's going on behind the scenes when compiling Python code and interpreting it. So tomorrow I will jump right into the exercises on page 51 here, and we will, um, yeah, we'll complete these exercises and move on with out of chapter one and on to chapter two, and take this little by little, day by day. And over the might seem like a lot of pages, a lot of problems, but I'm in no rush. Hopefully, you're not in either. Um, I'm here to just learn. I have my whole life to learn. Um, it's not this is not something I want to just skate by to get a job in something. I want to actually know this stuff and be able to use it well, and you know obviously that's the goal. So thanks so much for watching. We'll jump right in.